Hello, everybody, and welcome back. Today, we are continuing with fluid mechanics, and specifically, we will talk about manometers. Before we move forward, as always, I want to remind all of you with an engineering degree from outside of the United States, if you are trying to evaluate your education in the United States of America and you need a little bit of help, I have put together a PDF guide with step-by-step instructions on how to do just that. Just click the link below and you'll be able to download it for free. Now let's move on with our example for today. I want to point out a few things to remember when we work with manometers and with pressure in general. So manometers are used to measure pressure by converting pressure to an equivalent height of manometer fluid. And another important thing to know is that going downwards, pressure is greater, which means we have to add. Going upwards, pressure is smaller, we have to subtract. Another point is vacuum or gauge pressure. Sometimes in the problem, they will ask you to calculate that, and it's important to know what this is. So when you are asked, calculate the gauge pressure or the vacuum, you have to know that this is the difference between the atmospheric pressure and the absolute pressure in the vessel. So now let's move forward and solve our problem. Find the pressure in the tank from the manometer readings shown. Let's go to a FE handbook and find the formulas they are giving us for the manometer. And here it is. I will go downwards and make it a little bit bigger so we have this visible. So look at this manometer and let's apply this formula. So what do they do here? So pressure in this vessel, P0 equals to P2, right? And then remember how I was saying that the pressure increases with depth. So from this point, in order for them to get to this point, they have to add gamma 2 times 8.2. And now from this point, when you have the same liquid within the tube, you are allowed to go from this point to this point because the pressure horizontally is equal. So you're allowed to do that, to jump from here to here, but only when you have the same liquid within the tube. So now from here, what they do, you have to go upward, right? And going upward, remember the sign is negative. So you have to subtract the H1 times gamma 1. So this is the way you use to calculate the pressure in the manometer. And let's go back to our problem and try and solve this. So we have the pressure in the tank. This is what we have to calculate, right? So the pressure in the tank equals to, we're going to go to P atmosphere. So we're going to have P atmosphere. And then from there, we have to go downward. So I'm going to add, and we have our fluid in here. From this fluid is marked as fluid C, right over here. This is marked as fluid C, and we're given the density of the fluid C, 1,000 kilograms per meter cube, which is water, density of the water. So our fluid, this fluid C is water. So we have to add the density of the water or fluid C, I will put it, times G times H, which is 1 meter. Let me just put 1 meter right away. 1 meter. We right now are at this level over here, and manometers allows us to go from this level horizontally. The pressure is the same here as in here because we have the same liquid within the tube. So we can go from this point to this point. There's no need to calculate the pressure here. So we can go straight in this point, and the pressure is going to be the same density of the water times G times 1 meter. And from this point, we have to calculate the pressure from this point to this point. And if you notice, we're going upward, and what we know, going upward, the pressure decreases. So we have to subtract now, and we're going to have the density of liquid B times G times 0.3 meters. And going forward, notice how we have to again subtract, because we're going upward, the density of liquid A times G times 0.1 meters. Now let's calculate all this. P atmospheres is 100 kilopascal, which means 1,000 pascals, plus density of water, we have 1,000 kilograms per meter cubed times 981 meters per second squared times 1. It's kind of messy here, but minus, let me try and be more organized this way. Density of fluid B is 750 kilograms per meters cubed times 981 over second squared times 0.3 meters, and minus fluid A, which is 500 kilograms per meter cube times 981 meters per second squared times 0.1 meters. Let's calculate all that. Now, if you are confused about the units, pascals and kilograms, let's talk about that if you're confused. So the FE handbook tells me that 1 Pascal equals to 1 Newton over meter squared, right? And then if you go back to the newtons, let's go to units and clarify this a little bit. Here, so we have Newton over here, and then Pascal here. So 1 Pascal equals to 1 Newton over meter squared, and then 1 Newton equals to 1 kilogram over times meter over second squared. So if you write that down, 1 Newton equals 1 kilograms times meter over second squared. So 1 Pascal will be equal all this, which you can see are exactly the units we have here. So don't be confused of adding Pascal with kilograms over meter, because it's the same units. So let's move forward and calculate all this to see how much is the pressure in the tank eventually equals to. So let's start. We have 100,000 pascals, 1,000 kilograms, 981 multiplied, 1 meter multiplied, add, and we have 750, 981 multiplied, 0.3 multiplied. We have to subtract this, and then we have 500, 981 multiplied, 0.1 multiplied, subtract pressure in the tank. I'm getting it as 107.1 kilopascals. And the closest answer is B. Okay, that's it for today. I hope you found this video helpful. If you did, don't forget to subscribe and give it a like, because this helps people like you find me. Also, if you have any questions about this problem or about any other problems that I have solved before, don't hesitate to leave a comment in the comment section below. Keep up the good work on practicing the FE problems, and I will see you next week.